I've had a question sent in by Monica who asked me to go over some stuff about transforming to linearity. So taking a data set that's nonlinear and transforming it using a log or a reciprocal or a squared transformation, one of those things, to make data more linear. This is the basic idea behind transforming the data. Say we have a scatter plot that looks something like this. You can see that this is not really linear. This sort of follows this curvy kind of shape like this. See how that pattern there to those dots, to those scatter points, doesn't really follow a straight line? We've got that curve. So if we want to work out an equation for this line in the form y equals mx plus c, it's going to be okay for this bit because there's sort of a straight part there, but the rest of the line out over here is going to be nothing like what the data actually was. So if we wanted to put a straight line on it like this, we would need to do something to the data before this could be kind of a valid statistical thing that we could get some information out of. Because down here it's okay, this section, but then the dots kind of move away from the line over here. They're not sticking to this line sort of shape. So something in the form y equals mx plus c isn't going to do us much good because that's not the shape of this data. So what we need to do is transform the data so that it follows this straight line, so that it goes more along this straight shape. Now these bits down here are okay, but this is where we veered off course. These dots are all kind of going up in that direction instead of sticking to this straight line down here. So what we need to do is pull these back towards the line. Now in this graph there's a couple of ways we could do that. We could either make them go this way towards this line by expanding out this x-axis. If we shove everything over this way, if we make everything go that way a little bit, then all of these will be pulled that way. They'll all get pulled over this way and conform a bit more to this line. So it's something a bit like this. I'm grabbing the data and I'm stretching it out that way, which makes it follow more of a line shape. But there's something else I could do here. I could try and move them all that way by stretching out this x-axis, or I could try and move them down that way and smush them all down into this line. So that would be smushing up the y-axis. So there are two ways that I could fix this. I could make this data more linear by stretching out the x-axis, making it all go that way a bit more, or by smushing up the y-axis, compressing that down, because then they'd all come down here into this line. The problem is that they're above and they're to the left. So I could either make them go down or I could make them go to the right. We have a couple of sneaky little methods for doing this to data. To stretch stuff out, what I'm going to do is square it. So if I want to stretch out that x-axis, I'm going to square the x's. Now the reason for that is I don't really need to affect these early ones because they're kind of on that line already. They follow that shape. So let's say this is, 1, 2, 3, 4 going along here. 1 squared is 1, which means squaring the x's, 1 will stay exactly the same. 2 squared is 4, so that's doubled it there. It's increased a bit, but not by too much. 3 squared is 9, so now it's tripled itself there. It's gotten quite a bit bigger. 4 squared is 16, so now we're getting quite far away. The gap between 4 and 16, it's stretched quite a bit. 5 squared is 25, so now the difference between 5 and 25 is 20. This x has gone up by 20 when I squared it. This one here had gone up by 12. This one here had gone up by 6. So you can see by squaring, it's getting a bigger and bigger gap every time. 6 squared is 36, which means it's gone up by 30. 7 squared is 49. So this has gone up by 42. So the gap between them is increasing, which means that this x, if I change all my x's to be x squareds, so instead of 1, 2, 3, 4, 5, 6 going along this scale, I now put 1, 4, 9, 16, 25, 36 and so on. The 1 point is just going to stay the same because 1 squared is still 1, so that'll be in the same spot. But all these other points will progressively have to stretch out more and more going in that direction. And the higher the x value, the more it's going to have to move that way. So as a result, these higher values of x over here on the right hand side of the graph are going to get seriously stretched that way, but these ones down over here on the left are not going to stretch as much because they're lower values of x to begin with. So the end result of squaring this is that the higher values here are all going to move that way. These little values will move just a little bit, but they only need to move a little bit to get onto that line. This big stuff up here is where the problem was, because that was kind of all not on this line. So I need to move that stuff this way, and squaring the x's will have that effect. Now the other way that we might like to transform this data to sort this problem out would be to smush up these y values to make these guys conform into that line there. And we have two ways of doing that. If we want to stretch something out like the x, we were squaring it. To go the other way, to smush it all up, to make it kind of all these y values smaller so that it's all happening in a lesser span of distance, we would say 1 on y. We would take the reciprocal of y, or we could do a log 10y. So these are two ways of smushing up a scale. And the technical mathematical correct term I think they use is compressing. So what we want to do is compress the y data. We want to make it all smushed down here so that this chunk, which is not following our line pattern, will join up with the rest of everybody on this line. So to linearize this graph, our options are either to stretch out the x's to make this kind of these points, this general area, go this way, in which case we would use an x squared. Or we could smush up the y values. We could make them go down instead of to the right. And to do that, we would need to use 1 on y or log y. So here's another example. See how this scatter plot kind of follows this sort of shape? We've got another one of these non-linear looking shapes. And we want to put a straight line onto it. We want to make it follow this sort of a shape. Like that. But the trouble is, all this stuff is kind of, that works with that sort of shape. This kind of follows that trend. But we end up with this stuff over here, which is not playing along. Now the trouble is, we need this to follow up here. So we could do a couple of things to it. We could either stretch out these y's. We could make this all go up here so that it joins this line. Or we could make them go this way. We could make these all join up back over here more towards this line, which would be smushing up this x-axis. So for this one, we could smush x, or we could stretch y. Which means, what was stretching? Stretching was squaring something, and what we want to stretch is the y, so we would be squaring y. Or smushing was taking the log or the reciprocal. So if we want to smush up x, we could either do 1 on x, or we could do log of x. And say we were to do y squared, again, because squaring has a greater effect the greater the value is, as y is low down here, these low values of y wouldn't change very much. They wouldn't move up very much up the scale. But as we got bigger values of y, so as we go up this scale, these ones are going to get quite affected. They're going to move up even more than the distances that these ones are going to move up the scale as we pull this whole graph upwards. So the effect of that is that this stuff over here, which is our problem area, is going to move the most. It's going to go up towards that line that we want it to join. And the alternative is to smush x that way by doing 1 on x or log of x. And the same kind of effect happens there. The lower the values don't get affected as much, and the higher ones will get affected enough to push them back in line that way. So here's another scatter plot. This one's also nonlinear. It's following this shape. Like that. Nice and curvy. And we don't want curvy, we want straight. We want to make it look something like this. So where is our problem area? This stuff is sort of okay, but this stuff here is not following the trend. So what do we need to do to it? We either need to make it go down here like this, so it'll join up that line, which would be smushing up the y-axis. We want to make it go down there, so we want to smush that together. Or we could make it go that way. We could make it join up the line over here by moving towards the left. We would smush up the x-axis. So my options here are to either smush the x that way or to smush the y that way. So if I'm smushing in both directions, remember squaring was stretching it out, and smushing was to take the reciprocal or the log. So for this option, because I could smush either way, I've actually got 4 things that I could do to it, because these two are for stretching. And we don't want stretching. We're not going to stretch either of those axes. What we want to do is smush them. And here are 4 options for smushing. This is smushing x, and this is smushing x, and this is smushing y, and this is smushing y. And I should say compressing rather than smushing, but I just think of it as, smushing them all up. So for this looking scatter plot that follows this trend, we could smush either x or y. And because there are 2 ways that you can smush stuff up, we've got 4 options for how to transform this data. So to make this patch of stuff go that way, that would be smushing up x. So I could do 1 on x, or I could do log of x. To make it go this way, down here, this little patch of stuff that's not playing along, I could either do 1 on y or log of y. And the last example looks something like this. This scatter plot follows this sort of curvy shape like this. And we want it to go in a straight line like that. So where's my problem area? My problem area is here, because the rest of it, this stuff here is following the shape the way I want it to, but this stuff's not playing along. I'll just draw that line again so you can see what I'm trying to make it do. So here, this stuff is where we veered off course. I want to fix up this patch. Now, I could either make these y's increase so that it goes up towards the line like this, or I could make these x's increase so that it goes that way towards the line. So stretching out my y's would make this all increase that way. And again, small values of y down here, low values of y, wouldn't move up by very much. These would just move a little bit. But the bigger y got, the more this would stretch up here. So to do that, I could do a y squared. The alternative is to move them this way. I want to stretch out this x-axis so that they'll join the party, so that they'll go this way. And how do I stretch out the x-axis? The stretching thing transformation that I have is x squared. And because I'm not smushing in either direction, those reciprocal or log relationships don't apply to this arrangement. So I would either do y squared or x squared. And just to show you as well, if we had said the line we're trying to make this conform to is there, which would have meant that this was our trouble patch instead of being up over here, the same thing would still apply, because we'd either need x to stretch out that way, which would be an x squared, or we'd need y to go up there like that. We'd need y to increase that way, stretch it out, so we'd need y squared as well. So whether you put the trouble patch as here or as this stuff here, either way, to make it go into a straight line, we need to do one of these 2 transformations. So here's a nifty little table that summarizes all of that, and this is taken from the Christine McRae Further Maths textbook. When your non-linear scatter plot follows this sort of a shape, like that, then to fix it, to linearize it, to make it so that it'll work with y equals mx plus c, you either want to use x squared and stretch out the x-axis, or you want to smush up, you want to compress the y-axis by doing one of our compressing things, which is either the log or the reciprocal, 1 on y. When the shape looks like this, then we either want to stretch out the y-axis by doing y squared, or we want to smush up x by doing one of our 2 smushing operations, which is log and reciprocal. If it follows this shape, like this one, then we're either going to smush up x or smush up y. So we've got 2 smushing operations, and we can do it to both axes. So we might do log x or log y, or the reciprocal of x or the reciprocal of y. And that word that I keep saying, by the way, is reciprocal, like a recipe, but on the end. Just in case you see this on an exam, they might say, what would be an appropriate transformation? And they might say, in words, log squared or a reciprocal. If they say reciprocal, then they mean this, 1 over the variable, 1 over x or 1 over y. Okay, and this last shape going like this, well, we're going to stretch out y or stretch out x to fix this up, to make this more linear. So that would be either an x squared transformation or a y squared transformation. So now that we've got the basics of that out of the way, I'm going to go over the question that was sent in. This question comes from the Maths Quest textbook, and it's from exercise 3F, and it's question 2. And the question says this: the average heights of 50 girls of various ages were measured as follows. And then we have a nice table of data, and it tells us the original linear regression yielded this equation: height equals 3.76 times age plus 104.7, with an R value of 0.92. Okay, so that R value is not bad to begin with, but this is from the chapter on linear transformations, so chances are we can make it better. Now, part A says, plot the original data and regression line. Okay. Part B then says, transform using the log 10x transformation. And part C says, perform regression analysis on the transformed data and comment on your results. So let's start with part A, which wants us to plot the original data and regression line. So we plot this data from this table, and we plot this line, which is in the form y equals 3.76x, which is our age, plus 104.7. We plot that line on there and these dots, and we get something that goes in this sort of a shape. Okay, so even though this R value is 0.92, we can see this is non-linear. And our residual plot for that is going to look something like this. There's a point below, and then there's some points above like that, and then there's 3 more points below like that. So this residual plot is not random. Part B of the question wants us to transform the data using a log x transformation. So we're going to draw ourselves a table, and we're going to transform these x's. We're going to leave the y's alone, which is height. So height's going to stay exactly the same, but what we're going to do instead is we're going to have age, and we're going to take the log of it. So this is going to be log 10 age. Now you can do this on your calculator quite simply. Once you've had these and these entered into the lists, you can just go into another list column and say, I'd like you to take list 1, or whatever this list is, and do the log of it, and it'll fill these in for you automatically, this next line of the table along here. But I'm just going to draw this out again. So on my calculator, when I work out log of 9, which is what that x was, instead of putting 9 as this, I'm going to have log 9, which is 0.954, and then I have log of 10, which is 1. Then I have log of 11, which is 1.041, and so on. So there's the rest of that table. I've now transformed it. Instead of x, we've got log 10 of x. So let's see what that new scatter plot looks like. And there it is. Now, I happen to think this is a bit of a stupid question, because this still looks like it's quite non-linear. But what they're wanting you to say with this is, except for this point down here, this section here now quite follows this straight line trend. It does actually work in this straight line a lot better than it did before. So even though it does kind of still look non-linear, and if you did a residual plot, that wouldn't look random, what they're getting you to get at here is that we've improved the linearity of this graph. We've made it straighter than it was before. So we're on the right track. Now, part C of the question said, perform regression analysis on the transformed data and comment on your results. So we've worked out this new linear regression line. This is me doing the regression analysis. And the equation was height equals 117.2 times log of age plus 24.3. Now, if you're wondering why my scatter plot crosses here at close to 130, it's because this isn't 0. I've got my x's starting at 0.9. So this isn't a 0 point. This isn't where x is 0. So if I extended this out all the way down, this would be crossing at 24.3. Anyhow, the new R value, now that I'm doing a regression analysis on this transformed list data, I have an R value of 0.95, and this is greater than this. So I have linearized the data. I've made this R value better than it was before. So I'm going in the right direction. A couple of ways to test if I could get a better one might be to do some other transformations, like other than log, for example. But the question is just asking us to comment on this. So we've improved the R value, which means we have linearized this data. There is still a little bit of a nonlinear trend happening there, but we have improved this regression considerably. Question 4 from that exercise followed on, and it said, comment on the suitability of transforming the data in question 2 in order to improve predictions for girls under 8 or over 18. So there's that table again. And if you notice, our first point was 9, our last point was 18. So they're talking about extrapolating data either side of that. So within this range from 9 to 18, we did find a good trend. We found a regression analysis. We found something that we could use to predict data within that span, within that range. Looking at things either side of that could be quite different. And what this question is actually talking about, the fact that we're talking about age and height, do they follow a linear trend? Thinking about that logically in nature, your age, your height as you grow older, does that follow this kind of a shape? Maybe between the ages of 9 and 18, but when you're really young, you're really, really short when you're first born, and you grow really, really fast. And then it sort of tapers off. You grow a little bit slower and a little bit slower and a little bit slower. And then at a certain point, it kind of tapers off and you don't keep growing anymore. Like, what's the difference in height between someone who's 18 and someone who's 40? Not anywhere near the difference between someone who's, 0 or 1 years old and someone who's 9 years old, for example. So height in nature more follows this shape, your height according to your age. And this shape is a logarithm graph. That's what a log looks like. So y equals log of x looks like that. So applying a log x transformation to this data is really appropriate. If we're going to have to try and predict things either side of this, extrapolate below 9 or above 18, then a straight line graph is not going to work because that only works within this span. Either side of that, the graph actually will look more like this. And here's our little straight line patch between the ages of 9 and 18. But prior to that and beyond that, it doesn't follow that shape. So, comment on the suitability of transforming the data in order to improve predictions for girls under 8 or over 18. What I would say is age versus height is linear within this span, but non-linear outside of that. A logarithmic transformation or a logarithmic graph, logarithmic trend, is far more applicable to something like age versus height outside of those span of ages.